This chapter is called The Coupled Monsoon System. Basically goes through some results from the author of the book himself to argue about the feedbacks from the Indian Ocean onto the monsoon at various time scales. So this is not a textbook material in that sense, feels more like a seminar based on one's own results, but we will run through them because it has some good points that we should be aware of in any case. Starting with this one, where this is from a paper by Harry Hendon from 2003, where he looked at the relation between Indonesian rainfall and Indonesian temperature anomalies with the Indian Ocean and the El Nino. And the main point I wanted to take from there is that this, if you look at the spectra of the Nino 3.4 SST anomalies over this long period from 1951 to 1997, El Nino is very well known to have this quasi-quadrennial peak in its various variables, especially the temperature-based indices. But if you look a little bit to the west over the Indonesian region, this is the Indonesian temperature anomaly for the same period, and you see that there is a very strong biennial peak around 2 years, and then there is a much lower frequency peak over here at around maybe 8 years or so. So this is something that comes up in this chapter in terms of where this quasi-biennial time scale may come from, which is also seen in the Australian rainfall and over various Indian Ocean features, including maybe the Indian Ocean dipole and of course the South Asian monsoon. So that brings us to again reminding ourselves of the regression relation we had seen between the Nino 3 SST during November, December, January. So the regressed against Nino 3 itself and the monsoon, and here JJS precipitation was regressed against Nino 3 SST and itself. And obviously we saw that the Nino 3 SST has a high correlation with the NDJ during that season, which is marked here in this gray shade. And we saw that there is a hint of a quasi-biennial time scale in the regression with the monsoon rainfall over JJS. But the point also there was to confirm what Normand had suggested, that the monsoon actually leads the Nino 3.4 SST, and hence Nino 3 or Nino 3.4 SSTs may not be a good predictors of monsoon, but monsoon itself may be a good broadcaster of El Nino in some sense. And the same thing appears here, the quasi-biennial time scale of the monsoon and the phase lead lag relation between the Nino 3 SST and the monsoon rainfall. Okay, so we'll come back to this again a little bit later on. I wanted to just place the background states of the Indian Ocean in context before we go on to look at various quantities in the ocean, and mainly about heat transport and surface heat fluxes. This is a classic figure from Fritz and McCreary, maybe it's Schott et al. So Fritz Schott, Shengping Xie, and J. McCreary from 1997, I think, basically showing the wind stress fields from 1990 to 1998, along with the depths of the 20 degree C isotherm here from some ocean reanalysis called Simple Ocean Data Assimilation, SODA. Okay, shown for January, June, August, and November. So January and August are considered peaks of the winter and summer monsoons respectively, whereas the June is also Indian summer monsoon. November is the kind of a transition month, so it depends on how you define. People typically think of winter monsoons, summer monsoons, and intermonsoons, but here they're not exactly following that. So in the winter months we have strong northeasterly winds, the southeasterly trade winds persist, and you can see the thermocline corresponds to either the wind stress curl that's deepening the thermocline or the wind stress curl that's doming the thermocline or shoaling the thermocline, especially in this southwestern ridge we have talked about before, which is seen here pretty much in all months with a strong seasonality, as you can see. During the southwesterly months you have obviously wind stress curls deepening the thermocline over here, not so strong over here, and there are some details like the wind stress curl is positive to the north of the jet axis and negative, so positive here and negative here, so you can see a bit of a deepening of the thermocline here and shallowing of the thermocline there, but this is also related to the strong alongshore winds and the upwelling. So the seasonality of the forcing is a very typical and dominant feature of the Indian Ocean, which can be seen also in terms of currents. So this is the July-August currents showing the strong Somali current associated with this upwelling here, but if you look carefully, a low latitude jet that's crossing the equator goes unstable and creates many features like the southern gyre, and we'll see the issue of cross equatorial Ekman transport a little bit later on. It turns out that the way the winds are arranged in the Indian Ocean in terms of the easterlies and the westerlies across the equator, you can actually have Ekman transport smoothly going across the equator, which doesn't make sense when we say Ekman transport is proportional to 1 over F and F goes to 0 on the equator. Nonetheless, you have features like the southern gyre, the Great Whirl, there is a Socotra eddy on the north, and you can see the currents, the south monsoon current. So here is the Ekman transport shown, south equatorial current, north eastern monsoon current, East African coastal current to the south of the equator, and then I won't bother too much about these details, but we will see that the Indonesian through flow, which is coming across here, treks across and then goes down through the Mozambique Channel over with some Agulhas retroflexion here and some Agulhas outflow on the other side into the Atlantic as a part of the global meridional overturning circulation. All kinds of little details are there which we will not get into, but if you look at the other season in the winter, obviously you change the direction of the wind forcing and the coastal current. So Somali current is now southward, meeting the East Australian coastal current coming up from the south, and you have changes in the north monsoon current here with changes in the coastal currents as well compared to the summer monsoon months. Okay, so these are going to have impacts on sea surface temperature balance, the heat balance of the mixed layer, and of course cross-equatorial heat transports associated with the Ekman transports as well. So you can see the Ekman transport is southward here, but switches to being northward over here. So how does that relate to the monsoon circulation? The other big thing about the Indian Ocean is the meridional overturning circulation, which has great consequences about how the Southern Ocean communicates with the Indian Ocean. Since the Indian Ocean is closed off to the north, all the water has to get converted to surface water and go back out across the equator. So you can see that there is Southern Ocean intermediate and deep waters coming in, and they are upwelling over some time scales or diapicnal mixing and other processes, moving the surface waters back out. And there is a special feature here called the equatorial cell, which is related to having this special wind distributions and the Ekman transport across the equator seasonally changing. So those are the kind of details which I will leave along with this Indonesian through flow, which adds some complications, but we don't talk about much here in the context of the coupled monsoon dynamics. But there are many good studies that report on how the Indonesian through flow affects the mean state and the variability of the Indian Ocean. So we will leave that there and come back to the details of how the coupled monsoon dynamics works over the Indian Ocean. As I said, these are based on the results from Peter Webster's many studies, so in that sense it's not a fundamental textbook kind of material, but research material put in the context of some observations about particular time scales in the Indian Ocean and in the monsoon.